everyone, let's jump right into this. Welcome to today's explainer, where we're pulling back the curtain on what is easily one of the most incredibly complex, high-stakes environments on the entire planet, modern semiconductor manufacturing. Specifically, we're going to look at the hidden software brain that runs the show in a 12-inch wafer factory. Industry insiders call this the SIM, or Computer Integrated Manufacturing System. The scale of what we're talking about today is massive, and trust me, the numbers we're going to get into are absolutely staggering.
Right off the bat, let's talk about the price of admission. $16 billion. That's the estimated capital expenditure you need just to build a single 5-nanometer 12-inch wafer factory. Now, if you're wondering how one single building could possibly cost that much, well, you really have to consider the equipment inside. The most expensive machines in there are the EUV lithography machines. Just one of those costs roughly $300 to $400 million. And a factory with a capacity of, say, 50,000 wafers a month, it needs at least 20 of them. So boom, that's $6 billion right there spent on lithography machines alone. The investment is literally astronomical.
So what does a $16 billion price tag actually mean for the day-to-day operations? This is where the financial pressure gets real. Let's break it down using a standard 5-year depreciation schedule, though honestly, for top-tier companies, it might be even faster. At 5 years, the factory has to amortize $3 billion every single year. Divide that up, and it means the factory must account for $8.7 million a day, every single day. If that factory isn't generating at least $8.7 million every 24 hours, it is actively bleeding money.
Which brings us to the ultimate nightmare scenario. When you're running a facility under that kind of intense financial pressure, downtime is absolutely your worst enemy. $360,000. That is the cost of just one single hour of downtime if the factory stops producing. Let's break this down to the second, just to really put things into perspective. If the CIM system, that software brain we're talking about, crashes, the entire factory stops. Every second that ticks by costs $100. A minute costs $6,000. An hour is $360,000. Think about that from an IT perspective for a second. A single 1-hour software outage creates a financial loss equivalent to the entire budget of a medium to large software implementation project. If your system causes a 1-hour delay, poof, the entire value of your software project is wiped out instantly.
Moving on to Section 1, the core difference, humans versus automation.
Now you might be wondering, why is the CIM system so absolutely critical? Why can't they just pivot and have human workers step in if the software has a hiccup? Well, in the older 8-inch wafer factories, production was what we call semi-automated. If a system went down, human operators could actually step in, manually move materials around, push buttons, and just keep things limping along. But in a 12-inch, 300mm fab, it is 100% fully automated. It is completely paperless and entirely unmanned. There are literally no operators standing by to catch the ball if the software drops it. There's actually a really great saying in the industry that perfectly illustrates this reality on the factory floor. If the SIM system crashes, the factory stops. You can't just take a ladder to fetch a batch of goods from the sky car. In these modern fabs, materials are transported by these automated hoist transports, or OHTs, zipping along tracks on the ceiling. If the software fails, those overhead cars stop dead in their tracks. You literally cannot reach the products. Production doesn't just slow down, it's completely physically paralyzed.
All right, Section 2, complexity breakdown into logistics and big data.
Since there's zero human intervention, the CIM software has to manage absolutely everything. Let's trace how a digital order actually translates into physical movement. When an order comes into the ERP system, nobody reviews it. It flows straight to the manufacturing execution system to spin up a work order. But since there are no humans to grab the materials, the system has to instantly talk to the advanced planning and scheduling system to dispatch the task. That system then communicates with the material control systems and the overhead cars just to move the product to the right machine. And it has to calculate the absolute optimal path to get there, managing all the buffer zones so the incredibly expensive machines are never, ever waiting empty. It's a ridiculously delicate, high-speed ballet of data.
And what makes this ballet even wilder is what's actually inside those overhead cars. Back in the day, in an 8-inch factory, one lot, which is usually a box of 25 wafers, was typically just one single product. Nice and simple. But 12-inch wafers are so crazy expensive that factories now mix products. A single lot might contain wafers belonging to completely different orders. This means the SIM system can't just track the box anymore. It has to execute precise, piece-by-piece, wafer-level tracking across more than 1,000 different process steps.
All that micromanaging at the wafer level creates an absolute explosion of data. The system processing demand spikes exponentially. The number of active transactions jumps from maybe 3,000 up to over 30,000. But here is the kicker. Despite processing 10 times the data and checking thousands of machine parameters per second, the system's response time for a move in or move out command can never, ever exceed 2 seconds. Anything longer than that is unacceptable latency that completely disrupts the flow of the entire factory. Talk about pressure.
Let's look at another hidden layer of this puzzle: dummy wafers. Think about the physics for a second. Semiconductor manufacturing involves highly sensitive chemical processes and really specific airflows. You simply can't run a machine half empty. Every single slot in a wafer carrier has to be filled to maintain the environment. So they use blank dummy wafers to plug the gaps. Humans used to manage this. Not anymore. Now, the system has to autonomously track when to insert a dummy wafer, how many times it's been exposed to chemicals, when it needs a clean, and when it's so degraded it needs to be thrown out.
And then there's the whole issue of maintaining absolute precision. Look, production machines decay over time, no matter how advanced they are. In an older factory, you might do a manual pilot run to test and recalibrate a machine. Not here. In a 5-nanometer fab, the software uses an advanced process control mechanism called run-to-run. After every single batch of wafers, the system ingests the data, calculates the microscopic decay of the machine itself, and autonomously adjusts the parameters for the very next batch. It is literally correcting itself in real time. 0 manual pilot runs required.
Which brings us to Section 3, Zero Tolerance for Failure.
When you add up the escalating financial costs, the complete lack of human backup, the massive data loads, and the real-time adjustments, it leads us to the ultimate gold standard metric of this industry: 99.999%, 5 nines. That is the uptime requirement routinely demanded of a SIM system in a 12-inch fab. That equates to an allowable downtime of just 0.001% per year. Because remember, if one machine breaks down, okay, the factory runs at 99% capacity. But if the SIM system breaks, the entire factory, all $16 billion of it, goes completely pitch black.
So to tie this all together, this flawless software is totally non-negotiable because there's zero human safety net. The system has to flawlessly manage a massive, mixed product data load down to the individual wafer level. It performs its own real-time self-correction to keep decaying machines perfectly accurate. And hovering over all of this is a brutal financial reality where mere seconds of downtime cost thousands and thousands of dollars. Which really leaves us with kind of a mind-bending question to end on. We're building these entirely paperless, unmanned factories that essentially act as massive $16 billion printing presses for modern technology. And they are completely reliant on a digital brain making millions of decisions every single second. But in a world where complexity only ever increases, can any software architecture truly guarantee 99.999% perfection forever? It's an absolutely incredible engineering challenge, and it's the invisible backbone keeping our modern world running. Thanks so much for hanging out with me for this explainer. I hope it gave you a whole new perspective on the incredible, hidden intelligence inside our most advanced factories.